All right, so previously in Math 62, we looked at relative change, oops, wrong screen, or population in Washington. So I'm just going to hide this absolute change column because we really don't need it here. And what was important to us was that relative change, that we went up each 10 years by 13.56%. Now, usually when people make formulas with relative change, they'll probably do it yearly. And so what they would likely do is divide this by 10. We'll play with that some more later. And for now, we're just going to keep it simple. We're just going to say, hey, every 10 years it went up by about 13.56%. That gives us different results than when we went up by only 800,000 each year. Okay? Because each new population is bigger, and so the percent gives us a bigger amount because there's a bigger base. Right? So that's relative change. So what we need to do is we need to, on number 6, we need to plot that point we just calculated for 2020. And so if you haven't already done that, let's get that done now. We calculated in 2020 a population of 7,608,475. So 7.6 million. So estimate where that is on there. And just a note, the previous graph we did in absolute, and that came out to 7,500,000. So the absolute change bumped us up a little bit more 10 years later. Okay. Now connecting those, don't worry about using a ruler because there's a subtle curve, but it's very subtle because that's not a big percentage right there. So connect those dots to the best of your ability. Just freehand it. And then I just want to show you a couple other tricks on both Google Sheets and Excel. So let's get Excel up here. Whoa, that bumped it up. Yeah. But it's not, it's pretty straightforward. So we'll get some of it going in a minute. So here I have these points, and both Google Sheets, Excel, Apple has a program called Numbers for a spreadsheet. They'll all try to come up with some equation that goes through a set of points that you graph. And so I just want to review how to do that in both Excel and Google Sheets. So what I would do here is I've already got the graph made, so I click on the graph, and then I'm going to go in and edit it. So that brings up my chart editor here. Under Customize, series is your data. Okay, so that's in a spreadsheet term, the series are your data. So we have a series of years, and we have a series of populations. And what I want to do is put a trend line to it. Okay? So graphing, bottom line, is looking at some data. That data could come from a survey somebody did, it could come from measuring stuff, but it could come from some equation that we have. And plotting enough points so that you feel comfortable connecting the dots, saying, hey, look, I think there's a pattern here. Sometimes the pattern's obvious, sometimes it's not. The computer will try to apply this mathematical process to try and come up with some kind of equation there. So here, the first thing it does is it tries to make a line. And we can see those points don't quite line up. There's a curve to it, okay? A subtle curve to it. If we plotted more points, the curve would become more pronounced. But we only have 4 points here. So coming back into that, not everything's a straight line, and programmed into the spreadsheet are other options. So as far as the type of trend I'm trying to graph, the first guess is always linear. And then we can choose to do something else. So most spreadsheets, other options are exponential. Exponential is another name for relative change. So let's put that down in our notes. So we were looking at relative change in question 6 of our worksheet. Relative change is also called percent change. And another phrase for relative change or percent change is exponential change or exponential growth. And I'll review the reason for that. I went over that last time. So we'll go back over that in a minute. So back to my spreadsheet here. So my belief is since we changed by percent, this is an exponential problem, so I'm going to switch to the exponential. And when I do that, it looks like it's going through the center of each point. Now looks can be deceiving. It may be just a little bit off because those are pretty fat points, right, compared to the line. But this truly is an exponential pattern. So my guess is Sheets probably found the correct equation that goes through all three of them. And let's see, in Math 92, we'll go over how to figure out that equation. But I'm not worried about that yet. But the spreadsheet, it's kind of cool. It can do it for us. But sometimes it's good to know how things work. So I had to do an exponential. Other options are logarithmic. We'll talk about that in Math 92. Polynomial, we'll talk about that today. Power series, we'll talk about that today. Moving average, we won't get to talk about in either 62 or 92, but it's kind of cool too. So there's all these other options there. What else? Oops, I accidentally plotted something else related to. I turned on error bars. Okay. So now I have the graph in there. If I wanted to see the equation, again, I could ask for that by going back to Edit Charts and Customize Series. And one of the options down here is to label using the equation if we ever need it. And so it tells me what the equation is. And again, in Math 92, we'll figure out how they came up with that crazy equation. But I'm not worried about it now. All I wanted to do is just show how to plot some points the other day. But on our paper, we're going to try and model it. Excel. Excel is pretty similar. So I got to have some data. I'm not concerned about the absolute change. We're using the relative. That's how we calculated these new populations. I'm going to zoom out a minute so I can, ooh, wrong button. Zoom. All right. So here, Excel, I think the best way to make a chart is to highlight your data and then go to Insert and then go to Recommended Charts. And here it wants to graph a line chart. Now, all a line chart does is connects the dots. That's different than coming up with an equation for it. It's totally not the same thing. So I'm just going to scroll down. They don't have just points. So I'm going to shift over to all charts. And I want a scatter. That means plot points. And there it is for me. And so I just pop it in there. Once it's in there in Excel, then I can start editing the chart stuff. Like I might want some other titles on the axis. So if I click that, it'll throw them in there. Zoom in here. Oops, wrong button. Time maybe. All right. So here, once I pop those in there by putting the checkbox to show labels, it's always a good idea to put labels. We did that in Google Sheets yesterday. In Excel, once I get the labels in there, I just click on them and type over them. So these are years. And these are people. Always kind of freaks me out writing sideways like that. And up here, I might want to say this is the population of Washington. It's always good to label the graph when you look at it later. As far as getting the trend line in Excel, there's a couple of different ways to do it. One way is if you right-click on the points, you can click Add Trend Line. And then they added a new option over here where you can throw a trend line in. And then clicking that arrow there gives you the trend line option. So I can say make it linear, make it exponential. I can go back there to more options. And then it gives me these options here on the side. So if I wanted to see the equation, I could display it on the chart. And what should happen is Google Sheets and Excel probably use the same kind of math to do it. So whatever equation Google Sheets gave us, Excel should give us probably the same equation. So let's see, 91289 there. Oh, this gave us a different version. Interesting. All right, we'll explore that in Math 92. So back to our worksheets. All right, so you plotted that point. It was slightly higher than the other point. It's not quite a straight line because we have relative growth. Let's move on. So given that beta forms in different ways depending on the situation, there's a couple of main styles of equation that pop up a lot when people are analyzing situations or measuring stuff. So there's linear equations, that's absolute change. There's exponential equations, that's relative or percent change. And then there's quadratic equations, which is something totally different. Right? So we're just going to look at how to distinguish between the three of those. So linear. Linear is where we change by a fixed amount. Over each period. And the period could, oops, I got an extra letter in there. The period could be days or weeks or months or something else. And that change over the fixed period, that's the idea that we call slope. Slope is always vertical change divided by horizontal change. Yeah, and that's that rise over run. And in equations, we usually call that m. So if you see an m in an equation, it probably means slope. Right? It depends on the situation. So a typical equation, if we say our vertical variable is y and our horizontal variable is x, then the equation for a line, so we call that a linear equation, will most likely be y equals some number, that's the slope, times x, plus some other number, b.
That's my question. Are we only going to be in that form, or are we going to be?
This is the only form I care about. There's 3 or 4 other forms of a line, and some of those are listed on the worksheet. That is the way to calculate the slope, and I'm not so worried about that either, but I'll go over it. So here they have some different examples of lines. This one right here, if we solve for y, it'll look like what I call the slope-intercept equation, the one I wrote down there. This one right here, the slope is 1/2, and the y-intercept would be related to -3. This one right here has nothing added on, so that means the y-intercept would be the point 0, 0. So we're just going to be playing around with how to graph these suckers and how to distinguish between something that looks like this row and something that looks like that row. Now the big difference is each of the equations in the linear row is just something times x, something times x, something times x. Okay. Notice in the exponential row, the x is always in the power position. Now, sometimes we use a t for now, a t instead of an x for time. But if the variable is in the exponent, the power position, that means it's an exponential equation and it's not going to be a straight line. Okay, so we're going to look at how to graph that. Something that's quadratic, I'll explain the name quadratic, means there's a x is in the base, but there's a 2 as the power, just a 2 as the power. Back to my notes. A little more on lines before we talk about the other ones. So y equals m times x plus b. If I were to look at this graphically, if I pick any 2 points and I take a look at the rise and I take a look at the run, right? So the rise means go up. Sometimes it could be go down and then go left or right for the run. That fraction, whatever the rise number is divided by whatever the run number is, that's always going to clean up to equal whatever m is. And it doesn't matter which 2 points I pick. So if I had picked some other point right here, that's going to make a slightly smaller triangle when I go for rise over run. But these 2 triangles here, the small one and the big one, they have exactly the same shape. And whenever you take 2 triangles with the same shape and you divide similar sides, you always get the same answer. So it doesn't matter which triangle I pick, which 2 points I pick. The ratio of the vertical side to the horizontal side is always going to be the same. Right? And we'll do that, we'll show that with some examples in just a minute. The B here and here, that's a point on the graph. To get to that point, it means I didn't go left or right, so x is 0, and for y, we went up to wherever b is. So the y-intercept, that number b, is this point right here.
Your b is actually your y.
What's that? The b is the y value of that point. Yeah, the b is the y value of that point. Because if I'm on the y-axis, I have not gone left or right, so x has to be 0.
I always want to put the y in.
You always want to do what?
Put the y in the y spot.
What do you mean, put the
Like
y?
equals MX
The y-intercept and the y.
Oh, you want to put it over there
Yeah.
instead? Yeah. So, but here's the connection between those two. If you're on the y-axis, right? This is the y-axis. That means you haven't gone left or right, correct? So x has to equal 0 if you're on that axis. And if you look at this equation here and you plug in 0, you get y equals m times 0 plus b. Anything times 0 is 0, which means on the axis, y has to be b. Right? Only when x is 0, which means, again, we're on that axis there. Yeah, and it just takes getting used to, right? The more we do it, the more we get used to it. And in Unit 3, we're going to do lots of stuff with lines next quarter in Math 92. So we're going to get more used to it. Lines, again, are all about absolute change. And that absolute change is reflected in that number m. So like in the Washington population example, if we predict that the population is always going to go up by 800,000 people every 10 years, we're making it into a line. We're predicting that the population will change in a linear way. But it usually doesn't work that way. Well, lines are still important. All right, so we'll do more with lines in just a minute. So that's just kind of my overview of it. And again, we're going to spend all of Module 3 getting more used to this. We're just cracking the surface of it in this lesson. Next term, we'll do a lot more. So exponential is the next important one. If you zoom out on an exponential graph, it's going to look like a hockey stick, in my opinion. The graph will do something like this. It'll look kind of flat at first. It'll look kind of like a line, but then all of a sudden it just goes crazy. It just takes off. Right? And if we took that Washington population model with the 13% and looked out, a couple hundred years in the future, we would see it starts to make this hockey stick shape. Exponential equations, there's a few different variations of them, but they'll generally look like, I'm going to put a P here for like the starting population, times some base, and that base is raised to a power. So an example, a simple one, let's suppose a town is really booming and the population doubles every year. Then the equation might look like y equals, maybe they started at 1,000 people times 2 raised to the power x. And so if x was years, this would mean double that population every year, okay, if x were years. And so we'll take a look at a simpler version of this equation in just a minute. Exponential equations, again, they're all about relative or percent change. And so this base, b, that's related to our percent change. And I'll show how right now. We did this yesterday. I'm just going to go over it again. The B is also called, and again, this is something more for next term, but it's called a growth multiplier. Oops. Too many letters. A growth multiplier. Meaning when I multiply by that base, things grow. Right? So back to our Washington population example. Washington population, viewing the percent change as being more significant than the absolute change. We calculated that it went up about 13 points, I think it was 13.56 maybe percent every 10 years. So let's see, what was one of our starting? Was it 5,900,000? So we started at, say, 5,900,000. And then what we had to do is we had to get the next population, we had to add on to that 13%, so 0.1356, times that 5,900,000. Hang on, my pen's not working right. It's supposed to be sliding. We need stronger magnets and better tape. So again, this number right here, that represents our 13%. Right? The base, what you start at, that base is always 100%. So my new number, when I put those together, right, because I'm adding stuff up, is 113% of what I started with. And we tested that theory out yesterday by just multiplying 113% times the original amount, and we saw, yeah, that's the same thing as adding on an extra 13%. So let's just double check that right now without your calculators. Now, the 0.56 is rounded, so we'll just be in the ballpark of the actual answer. But if I whip out my calculator and I take 5,900,123, and I multiply that by 113%, that would have to be 1.13, and I'm going to throw the 5.6 in there. And what I should get close is close to the 6,700,000 that we started with in our data. Right? That was the 2010 population according to the US Census. Now we're off by 40 people because we rounded that 13% when we calculated, right? And that's going to happen. Generally, people round slightly differently to different places, so n values will be off a little, but in the ballpark, and we're in the ballpark there. Okay? So that base I was talking about back here, I said it's related to the percent change. It's related by comparing the percent change to 100%, which means what did you start with? Okay. So what that means is for exponential growth, if you start with a percent increase, and let's just call it R for rate, then the base for the exponential model is always going to be 1 plus whatever R is. So 1 plus 13% is a decimal. That gave us 1 plus 0.1356, which is 1.1356, for example. But you gotta, not exponential example, you gotta change the percent to a decimal to make all that work. And again, 100% is the same thing as 1, Reminder, what does percent mean? It means divide by 100, right? 1 out of 100. So 100% literally means 100. The percent symbol means divide by 100. And so that's that 1 I'm talking about here. So 100% is the same number as 1. Okay, so 1 plus the increase gives us the growth multiplier, which is just a quicker way to get the answer, right? Don't you agree that it's quicker to just multiply by this number on the base amount than it is to multiply and then add, right? This is a 2-step process, that's a 1-step process. So it speeds things up. And again, we're going to do more of this in Math 92. We're just getting it out there right now. All right, last one we need to differentiate between is quadratic models. Or quadratic equations. There are things like y equals x squared as an example. If I throw something up in the air and watch it fall, gravity's pulling on it. So the height of that pen comes from the equation negative 16t squared plus, let's say, I don't know, 10t plus 4. So this would be the height of a pen I throw. Height of a pen thrown up. The negative 16, that has to do with gravity. We figured that out by just throwing stuff and watching it fall and estimating its height. That's been thoroughly studied. The 10 here, that's the speed I threw it at. Speed thrown. And the 4 here, that's the starting height. Start height. Do you need to know all that? No, it's not going to be on the test. But this is just an example of an exponential equation, and a quadratic equation in reality. Other examples of quadratic equations, anybody have dish TV? Yeah, that dish is related to the shape of the graph that we get from y equals x squared. It's called a parabola when we graph it.
Quadratic equation.
Parabola is that U shape. Yeah, so if we graph something like that, x and y, we get this U shape like that. It's called a parabola. And if you spin that and to get a 3-dimensional bowl, that's a dish for dish TV. Yeah, and what is important about a parabola, it has a geometric property that anything that is aimed straight into it will reflect off, and no matter where you hit the dish, that reflection will always be in the same spot. So that little receiver that pops out and is somewhere over the middle, it's at this special point called the focus point. So that's why they're popular. So imagine if you had a pool table that had this shape to it, any ball you shot straight down into it and there was a hole right there would always bounce and land in the hole.
Okay. Quadratic equation always has x squared.
Yeah, so the key about a quadratic is it has an x squared. Now, let's think about this for a minute. Quad usually means what? 4. So why the heck, because this is a 2, why the heck is it called quadratic? And the thing is, if you consider x a measurement, then x squared literally means x by x. And I just made a square, a real square, right? And a square has 4 sides. And squares are related to area. So they got the name quadratic from the Greeks thousands of years ago when they were studying areas. They ended up, now they didn't use algebra like we do today, but they did some of the same stuff just in a different way. But from their study of areas, that's where the term quadratic came from. Because an area is measured in square units. Therefore, these things are quads. Okay. So that's where the term comes from. X squared is literally a 4-sided shape. That's what they're called quadratics. All right, so we just have to get used to, identifying the different kinds, and then we'll graph some. Oops, I said we'd get out early. Apparently I lied. Sorry about that. So here it says, how would you distinguish a linear equation from the other equations? So a linear equation, you just have a multiple of x. That's one. There's no powers, and there's no exponents. Okay, so those are some things I would say about it. Exponential equations, the variable is in the exponent. That's the key thing there. And a quadratic has a second power. Excuse me. So as far as identifying them, the first one, because it does have a second power in part 10 here, that would have to be quadratic. The next one would have to be what? Linear. And the last one? Be exponential, because it has a variable in the power or the exponent position. All right. Skipping on down. So they give some examples of lines here. Here's those hockey stick shapes I talked about. They call it a J shape there of the exponential. And on the next page, they show some quadratics, that U-type shape when you graph it. So those are the ways to differentiate there. So what I want to do is actually take some of this. So we're going to skip on down, skip on down, skip on down. You can go back and read that later. We're going to make some tables and build the graph. So let's start with this one right here, number 11. Get a quick sip of water. Grab this in here. So usually when I'm graphing, unless I know better, some numbers I pick to make my graph are usually I'll grab -1, 0, and 1. And then I'll think, do I need more? So I'm going to grab a quick drink. So plug in -1 here, figure out what y is. Plug in 0 there, figure out what y is. Plug in 1 there, figure out what y is. And then we'll decide if we need to graph some more points.
I have a question.
Yeah.
Like on the homework, it gave examples for us, and it was like -x + 2, and one of the x's was like -1.
Yeah.
Would you put that together so it's like a positive?
Yeah, so to be careful about that, anytime I plug something in, I always put it in parentheses when I plug it in, just to be safe with the signs.
Yeah, that.
So if your example had a -x, instead of writing -x when I was ready to plug, oops, that's not the eraser. Instead of plugging in -x, I would write it as negative parentheses, and if they said to put in a -1, negative times a negative would be a positive.
Right. Okay.
Yeah. Oh, I grabbed the wrong thing there. So yeah, erase that. All right, so let's see. What do we get here? I plug in -1. Negative times a negative is a positive. So that gives me 5/3 + 2. And then I think I would write this as there's a couple ways you can do it. Just whip out your calculator. 5/3 is about 1.67. Add that to 2, and we get 3.67. And I don't need an exact answer to throw it on the graph. And some of the homework problems say, state your answer as a decimal, not a fraction, because it's easier to graph that way. Did I get that right? 3.67? Anybody else get that?
Yeah. Or couldn't you just graph it without having to plug?
Well, so the question is, what does it mean to graph? And for me, it means to plot enough points so you feel comfortable connecting the dots. So I got to have some, could I just use the slope? Is that what you're asking?
Yeah.
Yeah, we'll do that in just a minute. Yeah, but first I just want to graph it by plotting points.
Would 3 2/3 work too?
Yeah, that's also an answer. Now on the homework, plugging mixed numbers into a computer is a pain because we write it like this, but we say it with a plus, and that's what it really means.
Yeah.
So computers get confused about what we mean by mixed numbers. So generally in the online homework, avoid mixed numbers. Use an improper fraction or a decimal. And most of these homework assignments say use decimals instead of fractions. All right, so I get, if x is -1, y is about 3.67, which I could also call 3.7 to the nearest tenth, because I really can't plot 100th on this scale. You with me? So 3.7 is probably good enough. If I plug in 0 here, 0 times anything is 0, plus 2 gives me a 2. If I plug in 1, I get y equals -5/3 times 1 plus 2, which is -5/3 plus 2. And if you whip out your calculator, you're going to get what? 0.33 maybe?
Yeah, I got one.
You got, or 1/3, yeah, if you have a fraction calculator. So this comes out to be 1/3. 1/3 can be approximated by 0.3 maybe to the nearest tenth. So I'm going to try and plot those. So let's say I have -1, 3.7. So that's going to be somewhere up here. I have 0, 2. And I have 1, 1/3, which is going to be around right here. Do those points seem to line up? Okay. So before I connect the dots, I'm just going to do this a slightly different way. I'm going to use the idea of slope. So the slope here is -5/3. And notice how I'm choosing to put that negative in the numerator. Because a negative number divided by a positive number gives me a negative answer. So -5, that's my rise, and the 3 is my run. So the way to use the slope is starting at the y-intercept, which is that point right there. The slope says to drop 5, 1, 2, 3, 4, 5. That's down. Run +3 means go to the right. 1, 2, 3. So the slope says the point 3, -3 should be on the graph. Does that look like it's in line with my other points? Yeah. Now this is a cool thing. If I take a positive number and I divide by a negative number, don't I still get a negative answer? So when I have a number like -5/3, I could view it as -5/3 or 5/3. This one says I'm going up 5. The run, negative means go left. So let me test that out. So from the y-intercept, if I go up 1, 2, 3, 4, 5, I'll be somewhere up there. And then I go left 1, 2, 3, I'll be right about there. Does that look like it's in line with the other points? Yeah. So the slope just tells me how to generate other points without calculating them using the equations. But either way, I'm going to get a line, something like that one right there. And so once you have enough points, then start connecting the dots. Now, some people say, hey, you only need 2 points to make a line, and they only graph 2 points. I usually do more than 2, because what if I screwed one of them up? I'm not going to know. And when I have negative sides floating around like that, I generally screw things up once in a while. So I usually do at least 3 points. If one of them doesn't line up, then I check them again. Okay. All right, so we're out of time for fun with this activity. So try to work on this on your own over the Thanksgiving break. You got a couple extra days off, and then we'll regroup and troubleshoot anything in the homework and the worksheet on Monday. This is lesson 2.7. We have up through 2.10. We're definitely not going to get to 2.10. We will get to 2.8, maybe 2.9. We'll see. So for sure, 2.10 questions will not be on the sample final. I'm going to finish right now. 2.8 will be 2.9, maybe. Let's see, because I'm not sure if we'll get there yet. All right. Have a great, safe holiday, and I will see you all in a few days. You're welcome.